So what the heck is happening here? It looks like this guy is holding his own head. Well, the answer comes from a physics concept called refraction. And refraction is the bending of light as it goes from one medium to another medium. Like when light goes from water to glass or from glass to air, it bends. And we'll have to explain why it bends or refracts. Before we do that, just another quick example. Laser beam going through the water here, and normally we think of laser beams going in just perfectly nice straight lines, but we can see that laser beam curving, bouncing off the bottom and curving here. In this picture I'm coming up at a little bit more of an angle, and we can totally see that laser beam curving or bending. I'll explain both of these today in this video. The reason light or sound or any wave bends is because it has different velocities in different mediums. So for example, we're talking about light here, and we use c because c stands for the word celeritas, which means swift or speedy. You may have thought we use c because it's a constant, but no, it's for the word celeritas. And in a vacuum, light travels about 300 million meters per second. It could circumnavigate the Earth 7.5 times in 1 second. But when that light hits air, it slows down a little bit. It goes about 92,000 meters per second slower in air than it does in a vacuum. And in ice, which is a little more dense than air, it travels significantly slower than what it does in air. Water is a little more dense than ice, so it slows down even more. Glass is more dense than water, so when light gets to glass, it slows down a lot more. It's going about 2/3 as fast. If this is 200 million and this is about 300 million, it's about 2/3 as much. And in diamonds, which are really dense, light is going to travel a lot slower, less than half as fast as what it does in a vacuum. So we can talk about the speed of light in different media, but there's another way we can talk about it as well. It's called the index of refraction. The index of refraction is simply the ratio of how fast light travels in a vacuum to how fast light travels in a particular medium. So the index of refraction for a vacuum is just 1. And I put a square around that because that's an important equation, and we are going to come back to that in a bit. But it's called the index of refraction. The index of refraction for a vacuum is just 1. It's exactly equal to 1 because the speed of light in a vacuum divided by the speed of light in a vacuum is just 1. The index of refraction for air, now that speed here is almost the same as there. They differ out there at 4 decimal places, or 5 significant figures. But often we say the index of refraction of air is 1, and it is 1 to 4 sig figs. So if you're using less than 4 sig figs, 1 is a very good ratio of the speed of light in a vacuum to the speed of light in air. Now we could do it for ice as well. It's just this number divided by this number, and we get 1.31. If we find the index of refraction for water, speed of light in a vacuum divided by the speed of light in water, we get about that number. Can you guess what we would get for the index of refraction for glass? Well, it's about 300 million divided by about 200 million. 3 divided by 2, about 1.5. And for a diamond, which is a little less than half as fast. In fact, if light traveled half as fast in a diamond as it did in a vacuum, this number here would be half as much as that number there. The index would be 2. Okay, so we can talk about how fast light travels in the different mediums, or we could talk about it in terms of the index of refraction. And it's the different speeds that causes light to bend, to refract. So if I'm going from air to glass back into air, light travels at a certain speed in air. It slows down when it gets to glass, and then it speeds back up when it gets into air, because that's just how fast it travels in air. And I'm showing this as a transverse wave, crests and troughs. One thing we can see is that the frequency, the number of waves that enter every second or go by this spot every second, has to be the number of waves that go by that spot every second. Just because it goes from air to glass, it doesn't change frequencies. The velocity slowed down, got smaller, so the wavelength would get smaller. And we can see the wavelength is indeed smaller. Another way to look at this, instead of showing the side of the wave, we're now looking more from a top-down view. And let's say every one of these black lines here represents the crest of a wave. Maybe you're dipping your finger into the pond. We're going to call these black lines here wave fronts. Okay, they're just the front of a crest of a wave. There's another way we can talk about this, and that's in terms of rays, like rays of light. So if we turn on a light bulb right here, there's wave fronts spreading out, or we could talk about it in terms of rays just going out from that spot. Both ways serve their purpose. One thing to know about the relationship between the wave fronts and the rays is that the rays are always going to be perpendicular to the wave fronts. Okay? Just those two things. So if I have waves coming here and they're spreading out and they're traveling at a certain speed in this medium, and then they hit a slower medium, you can see that the wavelength got smaller, but they only got smaller once that wave hit that new medium. So the waves that hit here hit after ones that hit more centered in the middle there. So let's look at the rays. So rays coming from this spot, again, are perpendicular to the wave fronts. What are the rays going to do when they hit the slower medium? Well, they're going to go off like this. And again, the rays are perpendicular to the wave fronts. Now, when we talked about reflection, we talked about waves bouncing off of surfaces, and we said the angle of incidence equals the angle of reflection. But now, if we draw in our normal to the ray and where it hits that new medium, this would be the angle of incidence. We're now going to call this the angle of refraction. And you can see that with a very large angle of incidence, it bent toward the normal. Okay, that was a smaller angle of refraction than incidence. And I built this little robotic car to illustrate this. This has these little sensors that shine down onto the surface and measure how much light is coming back. There's two wheels here, and each wheel is controlled by its own motor, which is triggered by the sensor. So when this sensor is on white, it makes the motors go fast. When the sensor is on dark, it makes the motors go slow. So now just a top-down view, we're going to draw this as a ray going from a fast medium to a slow medium. This sensor is going to hit the slow before this does. And you can see it kind of bent around like this as it went from one medium to another. It bent because one side slowed down before the other side. We have our angle of incidence and our angle of refraction. Notice that it refracted toward the normal when it was going from fast to slow. If I hit at even a bigger angle here like this, coming along like this slowed down, this is going fast, and it really bent or refracted a lot. It had a very large angle of incidence and then an angle of refraction. It was going this direction, but it refracted toward the normal. Now if instead of going from fast to slow, it goes from slow to fast, from one medium where light travels slow to one medium where it travels fast. Once those waves hit that new medium, they speed up. And so these are the wave fronts. Let's look and see what the rays are going to do. Remember, the rays are always perpendicular to the wave fronts. So they're going to go off at these angles here, and these are at right angles. So if I look at the angle of incidence, a ray was coming off in this direction here, and notice that it bent away from the normal when it went from slow to fast. And if it hit at a very small angle, it moved away from the normal, but just a little bit. And again, we can illustrate that with this little car here. This time it's going from slow to fast. This side's going to hit the fast while this is still in the slow, and it's going to just bend around there slightly, going off in a new direction. Angle of incidence, angle of refraction. If I come in at a larger angle, it's going to have more time going fast before that one gets out there, and then it's going to really refract or bend a lot. Okay. So we could also do this with just linear wave fronts. So this edge is hitting the slow and this edge is still in the fast. You can see that the rays were coming this direction. Now they're going that direction. That's going from fast to slow. Let's do it from slow to fast. This is going to be coming along here, hits the fast and speeds up while that was still in the slow, and the rays are coming like this and then going out like that. So let's see if we can actually develop an equation here. We're going to derive an equation that relates, this is the normal, we'll call this the angle of incidence on both sides, and the angle that it refracts at. We always measure those to the normal. So we're going to see if we can come up with an equation that relates angle of incidence and angle of refraction, the index of refraction for one of the medium, and the index of refraction for the other medium. Right? There's these two triangles that are formed there. And because the wave front is perpendicular to the ray, these two angles are going to be complementary. Whatever that is, this angle is going to be 90 minus that. And because the normal here was drawn in perpendicular to the boundary, then these two angles are also complementary. And angles complementary to the same angle are congruent to each other. So if this is theta sub 2, this is theta sub 2. And we'll do the same thing here. This was complementary angles, this was complementary angles. Angles complementary to the same angle are congruent to each other. So we have this green triangle with theta sub 1, this orange triangle with theta sub 2. And the length of this side is going to be how fast those waves were traveling in this medium times how much time it was traveling in that medium. And the side here is how fast it was traveling here. Notice it went a further distance in the same amount of time as here. That's because it was traveling faster in this white medium. All right. Both the green and the orange triangles share this common side. So we know the angle, we know the side opposite that angle, and we know the hypotenuse. So the sine of the angle is opposite over hypotenuse. That was for the green triangle. For the orange one, the sine of this angle is opposite over hypotenuse. Okay, so we can rearrange those, and we're going to move theta, the velocity sub 1 over down here, and velocity sub 2 down to there. This equals t over r. This equals t over r. They both equal t over r, so they can equal each other. Okay, and then I'm going to rearrange this equation here. I am going to just divide both sides by c, so that I get c in the denominator here. And then the same thing here. C I divided down here and moved over here to the denominator. So we have v sub 1 in the denominator here. I'm going to substitute that with v sub, or the index of refraction in that first medium divided by c. I'm going to put that here. And then for v sub 2, I'm going to put the index of refraction in that other medium divided by c. That's what I have here. Well, c cancels out, and this is the equation I'm left with. And I'm going to put a big ol' box around that because that is a really important equation. It's called Snell's Law. We can predict the angle that it's going to refract at if we know the index of refraction in one medium, the index of refraction in the other medium, and the angle that it was incident upon. Okay, and that was named after Willibrord Snellius, or just Snell. All right, so let's do an example of that. Let's say that we know it comes in at a 24-degree angle, and we want to predict at what angle it will refract. I can calculate the index of refraction for air and for water by taking the speed of light in a vacuum divided by the speed of light in air for this one, or the speed of light in water for this one. So we use Snell's law. The index of refraction in air and the angle that it makes in air, the index of refraction in water, and the angle that it made in water. So I'm going to divide both sides by 1. I'm trying to solve this equation. I really want to know at what angle it's going to refract. So you got to get theta sub air by itself. I'm not going to divide both sides by sine. I'm going to do the inverse of it. I'm going to take the inverse sine. The inverse sine of theta is just theta. And the inverse sine of all that is 32.7 degrees. I can predict, if I know the angle that it comes in, that it's incident, I can predict the angle that it will refract. So let's see if we can explain what's happening here. Light from his body is going from water through the glass and into air. It's going to refract a little each time, but the light from his head is coming just straight at us. So this is a top-down view, head and shoulders, water and air, and my eye. So his shoulders were under the water, and his head was above the water. So light from the head is just going to go straight through the air into my eye. And the light from the shoulders, if it came off at this angle, it's going to refract away from my eye. And I wouldn't see those rays of light because they're not going into my eye. But light's reflecting off those shoulders diffusely. So maybe some rays come this direction and this direction. They hit the air and they refract to my eye. So light from the shoulders came here and then in this direction, but I don't know that they were going this way, then that way. I just know they came from that way. So the light that came from here and there is going to look as if it came from there and there. That's how the body separates from the shoulders. Okay, and fish. When you look at fish underwater here, light is going from the fish through the water to the air, and one phenomenon is that the fish look like they're a lot closer to the surface than they really are. If you try to reach in there and grab the fish, you're actually going to be grabbing above the fish. We have depth of perception because we have two eyes. So when light reflects off that fish and comes off like that, it's going to bend away from the normal just a little bit. So where this ray of light and that ray of light look as if they originate would be right here, is where I would see the fish. So if I grab into the water and grab this thing, you're just grabbing what you see, but that's where the real fish is. Keep that in mind next time you're trying to grab a fish. Now this is a test tube that's made out of Pyrex glass, and it's surrounded and submerged in mineral oil. And mineral oil and Pyrex glass have nearly the same index of refraction. So watch what happens when I do this. I lift it up and we can see it. Now something funny happened there. There was a little bubble that formed for a second, and then once that bubble popped, then that test tube does not stop there. That test tube goes all the way down into the water there. We can't really see the test tube because the index of refraction for Pyrex and the index of refraction for mineral oil are nearly the same. Light goes just straight through that without refracting. So let's say that this darker gray is the Pyrex, the lighter gray is the mineral oil, and the white is air. So let's look for this one. That's like from here up. Okay, light that comes from the background of the people there, the pioneers in physics, light is going to bend a little bit, and when we're standing over here looking at it, it's all distorted. It comes from different places, and that's what allows us to make out that shape. But because mineral oil and Pyrex and mineral oil and Pyrex and mineral oil all have the same index of refraction, the light just passes straight on through. There's no distortion. So if we looked here, we can definitely make out the flask that's in there. We can see the letters and we can kind of make out the edges, and that's maybe clear. But did you see the whole beaker that was hidden in the beaker? Okay, maybe not. And when we drop that back inside, it just disappears because it's not refracting the light. It's not bending the light because they have the same index of refraction. And fiberglass is a neat thing. Fiberglass is a really strong fiber that turns invisible when you pour resin over it. So if we had this fibers in this woven cloth that's super, super strong, when we pour resin there and saturate that cloth, the resin and the fibers are chemically engineered to have the same index of refraction, and it makes those fibers just disappear. You can't see them. They're there, they're still strong, but it makes the wood a lot stronger. Okay. Now this is a problem we just did a bit ago. We said it came in at a 24-degree angle and then refracted at 32. Let's do this again, but instead of plugging in 24 here, we would plug in 8 degrees, and we would solve and find that instead of 32, it was 10.7. So it comes in at 8, refracts at 10.7. If it came in at a 16-degree angle, 21.5. We're just doing that same thing using Snell's Law. Came in at 24 degrees, refract at 32. Come in at 32, refracts at 44.8, so on and so forth. But here's the thing. Can you see that we're going to run out of angle of incidence before we run out of angle, I said that wrong. We're going to run out of angle of refraction before we run out of angle of incidence. We can still come at a larger and larger angle of incidence, but what's that light going to do? Well, one thing we can do, we can calculate the angle that it will refract at 90 degrees, the transition from one thing to another. So this time I'm plugging in this 90 degrees and the angle in air, because this was 90 degrees and this was the index of refraction for air, and I can solve for this angle of incidence, and I find that it's 48.8 degrees. We're going to call that the critical angle, theta sub c. The critical angle is the angle you have to be incident upon to have it refract at 90 degrees. Less than the critical angle, the light's going to refract out. But if I am incident upon that boundary at an angle greater than the critical angle, it refracts so much that it reflects. It's going to actually bounce and reflect back down inside the medium. Okay, and I come here, and the angle of incidence would equal the angle of reflection. It's just like it's behaving like a mirror. And I can illustrate that with my little robot car here, but I'm coming in at a very large angle here. This hits the new medium, and it whips all the way around before that ever got a chance to get out. I'll show it one more time. That's pretty cool. So if we hit at a large enough angle, all those rays just bounce off and go right back into the surface. So here is a triangular prism, and light from a laser is coming in this way. It's refracting here and then refracting out here. And I'm only looking right now at what's happening on this boundary. This is the angle of incidence, and this is the angle of refraction. Watch what happens as I get greater and greater angle of incidence. This refracts closer and closer and closer and closer to 90. And when it refracts just parallel to that, that's when we have the critical angle. This is the angle that it made it refract at 90 degrees. It's called total internal reflection. And you can see just barely right there that some of this light is reflecting into it, but a lot of the light is refracting out. And watch what happens to this light here. It's going to get brighter and brighter and brighter because more and more of it is coming inside. And once we go past the critical angle, then all that light reflects back inside. And again, that's called total internal reflection. So the laser beam, as long as I hit the boundary from slow to fast at an angle greater than the critical angle, it totally reflects back inside. You can do that like I just did, or you can do it with a stream of water, and this is just a hole drilled in a can, and water is coming, or the laser beam is coming out the hole and the water is, but the laser beam just follows the path of the water. And that's how fiber optics work. Fiber optics are really, really pure and clear fibers, so that once light comes in, it's just going to stay with that fiber. And you can pulse or modulate the light to transverse a signal. This is a pretty neat picture where I put my phone, my camera, under the water. of the bathtub and shot up at an angle. A little hard to tell what's going on in that picture, but this is the surface of the water, and all in through here, the surface of the water is behaving like a mirror. That purple line there is the critical angle, where the light reflected back toward the camera or the light was able to get out. Let's look at the side view and see if we can tell what's going on. So this is the water level up to here. If light came from these spots here, these rays are going to make it out. These rays reflect back in, and it looks like the critical angle is somewhere in through here, either refracting out or reflecting back in. But light's not coming from right there. Light's coming from these other spots. So light from those spots are going to reflect off and come in. So if I look less than that, it's behaving like a mirror. So everywhere along here, it's behaving like a mirror, and everywhere greater than that angle is, or less than that angle, is light is getting out. So there's that picture one more time so you can see a little bit about what's going on. We've only looked at examples where it's a definitive boundary from one medium to another, from slow to fast, and it's a very sharp, abrupt bending of the light. But instead of going from one into another, we're going to have gradual changes. It's going to refract a little bit at each change. Or instead of that, if it was just a continuous gradient, then it would just be this nice, smooth curve. And that's what is happening with that other picture I showed you with the laser beam bending. You can take this tank and put a little bit of pine sol oil in there. It'll make it so you can see the laser beam in the water. Once the pine sol is in the water, drop sugar cubes lining the bottom here. Don't stir it up. Let it sit overnight, and the water is going to dissolve the sugar cubes, but it's going to be a gradient from dense sugar water down here to more pure water up top there. And that's what made the beam curve, is that light travels slower in dense sugar water than it does in pure. There, it was a gradient. And that's why it was going faster here, slower there, it curved down. That same picture again. This time we're going to have the slow on the top and the fast on the bottom. So it's just going to curve like this. Okay. Now, like if this is asphalt, dark material that's going to absorb the sunlight, air next to that is going to be really warm, and air higher up could be cooler. And that's what makes mirages. The air that's right next to the asphalt is very warm, and air higher up is going to be cooler. But light coming from up here, coming down toward the surface, curves back up to my eye, and the surface is behaving like a mirror. Just like from the car, curve down and back up to there so we could see the car. Or if it was light from the sky or something else, just the surface is behaving like a mirror. Now this is not light reflecting off the water. This is warm water, so the air next to the water is warmer than water higher up. And that'd be the boundary, the reflection line of that ship. As if the water is warm. Okay? If the water was cool, and we had warm air high and cooler air down lower, let's say that this is all the same temperature, so the light just from that ship can come straight over here. So it was going through the same temperature, the same density of air, kind of all the way through. I would look at the ship and I could see it right there. But light from there is reflecting diffusely. Maybe some of those rays are coming up toward that gradient and curve back down toward my eye. So I could have green light coming to my eye from here and white light coming to my eye from there, brown from there. I'm going to look and see where that light came from, and it's going to look as if it came from there. I would see a reflection of the ship in the sky, and there's some pictures of that happening. The air higher up is warm, the water is cool, and you could maybe just make out kind of the boundary between the cool air and the warm air. And this is a picture I took of the Kenai Peninsula looking out over Cook Inlet. And the water was very cold, the air next to the water was cold, but there's that reflection in the sky of that island out there, the peninsula out there. Another really interesting thing that can happen is if the ship itself were beyond the curvature of the Earth, so you wouldn't be able to see the ship itself, and this was the fast air and cool air where it was traveled slow, light could bend all the way around to here, and if I looked off in that direction, I would see the light that came from here. I wouldn't see the ship itself because it was below the horizon, but I would see the ship flying above the horizon. And there's a neat picture that's been circulating around recently, and it's pretty darn neat. That's a little bit about refraction, and I hope you enjoyed and hope you learned a lot today.